Yes, Kashiraj, if you have any question, you can ask.
Hello, sir.
Yes, please.
I have one doubt, sir, regarding this ADC flash type ADC analog to digital converter.
Mm-hmm.
So, in lecture number 14, time 30.19, around 30.19. So, this N for N bit N bit flash type ADC, how much comparator is required, sir? Opium. Actually, in that video,
Yes.
sir told that for N bit flash ADC,
Yes.
flash type ADC, N bit comparators are required.
Yes, right, right, right.
N bit comparator required, sir.
Yes, yes. Just hold on. Let me check.
Actually, for 2 bit, sir taken two bits at the like 00011011. So, sir used their 3 comparator. Op-amp as a comparator. So 2 bits means here 3 comparator required, no sir?
No, it is not exactly. I see when the number of, let's say, when the number of bits are very high, so at that time also require that much. So
Uh,
just let me check.
okay sir.
Yeah, I think it is two n minus one.
Hello sir.
Yes.
2 raised to n minus 1 comparator required sir.
Yes, yes.
But sir told in that
Yeah,
n bit
let me see what sir has said.
at 13.19 around 19 30 minute 90 second. The sir told like that in that video.
Just hold on.
Okay, sir.
Week 4, huh?
Week 4 second lecture, sir. Week 4
Acha. So
second.
lecture number 14, right?
Yeah, sir.
Yes. So at what time? 13.
13.19 somewhere. When sir talking about
Flash
this
type. Yes. Yes.
flash type ADC hardware complexity.
Just let me check.
Okay, sir.
No, baby. See, what I feel is maybe what he has.
He told n bit op-amps required, but here op-amp we are taking comparator, no sir.
Yes, 1 bit op-amp is required, but then did he mention 2 to the power n?
No. He said that for n bit ADC, n bit comparators are required like that.
Okay.
In hardware complexity, it is written, sir, in video. While discussing the
Complexity, huh?
hardware complexity of this flash type ADC.
Just let me check. Can you tell me the exact timing? I am not able to find. If you can, you are in front of your computer.
2 minutes, sir. 2 minutes.
Yeah. Yeah.
Hello, sir.
Yeah. Tell me.
At 30.24, sir, video.
30.24.
24:23 you see, sir.
Hmm. Just hold on. Yeah, I think it should be 2 to the power n.
Okay, sir, but there is sir written like that. That's why I asked, sir.
So, mm,
Okay, sir. This assignment number 4, sir. Question number 7. That question is like this: the CMOS sensor is having more power consumption as compared to the CCD,
yeah.
but actually the CCD is having more power consumption, no, sir.
Yes, yes, yes.
Then
No,
that what
that I
about
think we
the
have discussed last time, no?
last time we discussed, but what about this question, sir? Assignment number 7 for question number 7. So question is wrong means how will we evaluate that question, sir?
Can you post that in that forum? Because I don't have, the problem is I don't have access to the forum. That is the problem.
We already I already posted, sir, but
Hmm.
no reply, sir, regarding that. Question is that question is wrong, no, sir. Power consumption of CMOS sensor is more than CCD sensor.
Hmm, hmm, hmm.
So that question,
That's okay, but for example, if you consider the power consumption of CCD sensor is more than CMOS, then can you answer that? If you reverse the question, can you answer that now?
we can answer, sir, but here they given like this, no question we can't change, no, this
I
assignment type.
understand, but they are asking, they are not asking whether it is true or false. They are asking it is why. So just mark the ones which you feel is correct. For
Uh,
example, that see here they are not asking something, asking you to tick, okay, whether CMOS is having more power than the CCD. What they are asking you to tick is the fact. Okay. Now the fact is whether CMOS sensor have embedded logic in them.
uh,
Okay. So can you just tick the correct ones? Forget about the questions. You treat all these four options just as statement.
okay, sir, no problem, sir.
Got it?
Okay, sir.
Yeah.
Okay,
Because
sir.
right now, without someone correcting the question, you have to
Yeah.
take some answer, right?
Uh,
That is the
that, that is right, but sir, but we will get less mark now for assignment. That is a problem.
no. I am saying that can you write, for example, let's say that whether CMOS sensor is having embedded logic in them. Treat it is like whether it is true or false.
Okay, sir. Okay, sir.
Out of the statements, whichever is true, you can mark.
Okay, sir, no problem, sir.
Okay.
Then can you explain resolution, sir? For suppose n bit,
Yes, yes.
how much be the resolution
See,
for
resolution
n?
is normally, for example, let's say you have 5 volts, right? It
Okay, sir.
is getting converted to 255. Okay.
Uh,
So,
so,
how much each bit corresponds to? That is
yeah.
meant by resolution.
So for 8 bit means we have to take 2 raised to 8, sir.
2 raised to 8 minus 1. Because, see, this 2 volts, I mean, what you have to do is 2 divided by 2 to the power n. Yes.
2 to the power 8, sir.
Yeah, yeah.
Suppose 5 volt is there and 8 bit.
Just hold on, just hold on.
Okay, sir.
Hello. এই আমি এখন ক্লাস নিচ্ছি, বলো বলো বলো, কোনো ব্যাপার নেই। হ্যাঁ 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 হ্যাঁ, ঠিক আছে। হ্যালো।
हाँ सर, for
Yes.
if suppose their maximum swing is 5 volts, sir,
Okay.
and 8 bit, if suppose 8 bit is their resolution,
Yes.
then we have to take 5 upon 2 raised to power 8, sir.
Yes, yes, yes.
Okay, sir. Thank you, sir. Thank you, sir. Okay, sir. And one more question, sir, regarding this delta sigma.
Actually, the way you should take the resolution is 5 divided by 2 to the power 8 minus 1.
So you have to take 2 raised to 8 minus 1, sir.
Yeah, so it is 255. Yes.
250. Okay, sir. Okay.
Yeah.
Okay. Thank you, sir.
Yeah.
And this delta sigma modulation, can you explain, sir, in short, sir? This
Yeah.
delta
So,
sigma.
delta sigma modulation you want or delta sigma ADC you want?
Delta sigma modulation in ADC, sir.
Yeah. So if you see, just hold on.
Okay, sir.
In which lecture it is?
This lecture, I think they are not mentioned in that lecture, sir, but in assignment the question is there on that delta signal modulation.
Yeah. See, okay,
Yes.
then let me bring my pen and paper. Okay.
Okay, okay, sir. Thank you, sir.
Yes, are you able to see my screen?
Yes, sir. Yes, sir.
Yeah. So see, in delta sigma modulator, what happens is, let's say you have a signal which looks like this. Okay. Now, if you zoom into this part and if you check, then it will be something like this. So normally, what happens? Let's say you quote the first value. Okay. The first value. After that, what you do, instead of taking the sample here and coding again from the start, what you do, you take this portion. Okay. If you zoom into this portion, what it means is you have coded this portion, right? And
Yeah.
you may code this portion, but instead of sampling it and coding it again, what you do, you store this value. Okay, you are storing this value. Okay, after you store this value, what you do, you check only this difference, del.
Okay, sir.
Okay, and then after del, after digitizing it, after you digitize it here, you store the digitized value of del with this value, stored value.
Okay, sir.
Okay.
Means this process is a iterative process, sir. Again, repetitive. We have to repeat same
Yes,
thing
yes,
again
yes.
and
This
again.
process has to be repeated.
Okay, sir.
This
Okay.
has to be repeated. This process happens for all everything. So here you check. So this way, this process happens for everything.
Okay, sir. Thank you, sir.
Yeah,
Okay, sir.
you got it, no? So this is one point. Yeah, this is one point. So this is, if say del, then this is transferred to some stored value.
Like sample and hold circuit, sir.
Correct. Is there? Yeah.
Okay, sir. Thank you, sir.
Yeah.
Okay, sir.
Anyone else? Any question?
This method is also called as recursion.
I won't say, see, yeah, recursively you can say. But see, this is not exactly called recursion. Recursion means that, for example, is something that you use in machine learning or in C, where you call the same function again and again. Okay, I won't say this is recursion. This is iterative. Okay, so what it happens is you first have some value. Okay, now you store this value. Now based on this stored value, what you do, you take only the change, okay, whatever is happening del, and you add del to the stored value. Okay, instead of generating all the bits again from the start, what you do is you store the initial value and then add or subtract the new value. That's all. So I would say this is an iterative method, not a recursive method. Is it okay?
Okay, sir.
Yeah. Anyone else? Any questions? Okay. Today we'll discuss some questions. So let me know if when you can see my screen. Okay. Can you see the screen?
Yes, sir. Yes, sir.
Okay. So can you start doing the questions? I mean, for example, what will be the answer of the first question? I think you have already done this, but let me revisit all these questions because it will be good for you. So can anyone tell me what is the answer of the first question? Hello. Yeah, I would really appreciate if people can speak, okay, because I cannot see the screen all the time when I'm in that PDF. Yeah, anyone else?
Main memory, sir. Main
Sorry?
memory.
Yeah, yeah, Shiny is saying C, but anyone else who would like to contradict? Okay, yes, it is right, it is C. Okay, and after that, let me come to this. Okay, can you tell me the true and false? The first one. The first one. No idea. What are IO map systems? True. Okay, Poppin says true. But what exactly are IO map systems? Can anyone tell me? The IO map systems are systems whose assembly codes are different from, the assembly codes for memory fetch and read and write are different from IO fetch, read and write. Okay, so you have separate instructions. You have separate instructions for IOs and separate instructions for memory. Now this becomes a problem because when you are trying to compile a C code and making a binary out of it, you need to write separate programs to access the input output, and you need to write separate programs to write the memory access. Okay, so this is a microcontroller. So the second one, a microcontroller integrates multi-chip systems into RAM, ROM, IO. True or false? This is pretty straightforward.
True, sir.
Anyone?
True, sir.
Correct. Okay, I will change this tab. Okay, what is the next, whatever is the next part, I'll change this tab to, first of all tell me whether this is correct, true and false, then I will change this question, I will make it heap, and then you tell me whether again it is true or false. So you know, right, what is stack? Can anyone tell me what is stack, or else I will explain. Can anyone tell me what is stack?
We stand the person to operations at this power.
Yeah, tell me. It follows FIFO principle, sir, which is correct, yes. And rest, someone else was telling me. What someone else was saying? Please be loud and tell me. Tell me one thing, I'm just writing some code. Okay, maybe you can see. Let's say that you are writing some program, okay? Uh, main int a, int b, char c. Okay, so which portion of this will go to stack and which portion of it will go to RAM? Can anyone tell me? Suppose you have written a program like this. So this is a global variable, and these are local variables. So which portion will go to RAM and which portion will go to stack? See, RAM and stack both are same, okay? Because stack is a part of RAM. So you must say that if someone asks like this, which one goes to stack and which one goes to RAM, all of them goes to RAM, okay? But out of all these three goes to stack, okay? Because these are internal variables or local variables, okay? So you have to understand this, okay? And what is heap? You should know as embedded system, as a part of embedded course, you should know what is heap. Any idea what is heap? Anyone? Any guess would be fine, okay? Any guess?
Hello, sir.
Yes.
Basically, stack follows last in first out.
Last in, yes, sorry.
Yeah.
Yes. Stack follows last in, first out. The last to be in is the first to be out. Yes.
Yes, sir.
Yeah.
And heap is a type of a tree type structure, I think.
Yes, but can you tell me from the embedded point of view, at what situation heap is called? Heap is used. For example, can you in this program, can you say heap is being used?
Don't know, sir.
Yeah, okay, fine, no problem. But it's good that you tried. See, this portion goes to stack. Now, have you heard of functions called malloc, calloc?
Yes, sir. It's a type of dynamic
Dynamic memory allocation,
Yeah.
exactly. So, dynamic memory allocation follows heap.
Okay.
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 So, whenever you have a microcontroller, you have this RAM, right? In this RAM, you have all this data. Okay. Then you have something called stack, right? And then whatever is the leftover memory, it can be called as heap. Okay. So when you dynamically allocate the memory, your memory is taken from heap. Okay. So maybe I'll up the questions. So, do you have any doubts with the existing video lectures and all? Okay.
Sir,
Yes.
regarding the power consumption, which you discussed starting in the seventh question about that, the power consumption of the CMOS sensor is less than the CCD, but sir have mentioned, I think twice in the lecture that CCD consumes low power than the CMOS.
Yeah, I understand, but the point is here there is several things. Okay, see the lectures that you are seeing right now, they are very old. Okay,
Okay.
so they are around 2005, 2006 lectures, or maybe before that also, and
Okay.
later than that. And there has been several advancement in CMOS and CCD, and right now CMOS is really low power, and
Yes, sir.
it consumes lesser power than CCD.
Okay.
Okay, so that is the reason maybe you are saying that, okay, so what sir at that time when he was teaching, maybe at that time it was higher, but right now it is much
Yeah. I think at the time CMOS was in the beginning stage.
Yes,
Maybe.
exactly,
Yeah.
exactly. Yes, yes.
Okay, so.
But CCD was long there. So right now CMOS, because of the nanometer technology, CMOS power has drastically come down.
Okay.
That is the whole idea.
Fine, sir.
Okay. Yeah. And why only Shiny is answering? What about others? Can anyone answer with this question? Sorry, this one, question 2. So what would be the output? What would be the option for question 2? See, Gatsky's star chart, if you see, it deals with the hardware realization, okay?
Is it XOR B?
Exactly, exactly, yes. It is XOR, okay? It is XOR, okay? So, I think this you know. This you already know. Let me discuss 4, right? Wait. Let me open 4. Yeah. Can you answer question number 2?
Low pass filter, sir.
Yes, low pass filter. Okay. So, uh, mm,
High pass filter.
sorry.
High pass filter.
Acha, why do you say it's high pass filter?
Uh, Sir, because digital signal resists the means noise. I think.
Hmm? No, tell me. I couldn't understand.
High frequency can be removed. Possibly particular.
I'm not able to hear you.
So high frequency can be reduced. I mean, eliminated. High frequency.
There are two things to it. Okay. So one point is this: when you say it restricts the input. Okay. When you say it restricts the input, are we making the input 0? So what it actually means is, you whatever input is there below a certain frequency limit, you are only allowing it to pass. Okay. So for example, if you have some uh, some frequency spectrum which looks like this, you are allowing only this portion to pass. Okay, only this portion. Now this is possible only through a low pass filter. Any doubts in this? Any doubts? So you have to understand what is meant by restricting the input. Means you are allowing only that input to pass. Okay. So question 3, an operational amplifier. Okay. So this an operational amplifier has what? Very low input impedance and infinite output impedance. Just study the 4 options and tell me.
See, sir. See, input impedance in operation amplifier is very infinity. The ideal condition.
I'm not able to hear you. Can you?
In ideal condition, op amp. Hello.
Hello.
In op amp, in ideal condition, infinity impedance and low output impedance.
Yeah, right. By the way, pop-in, I mean, that is what is appearing here. Your voice is very low. Just try to speak loudly or keep the microphone near your mouth.
Okay, sir.
Yeah, but yes, you are correct. This infinite input impedance and very low output impedance. Okay? That is precisely the reason that you can put op-amps, one after another and achieve some functionality. Okay, because that is the reason it behaves like a linear system. So question number 4, the number of comparators needed in a flash A to D converter for a 5-bit conversion is
31.
correct, 31.
31, sir.
Correct, 31. Okay. Yes, question number 5. You may need to calculate. Can you calculate and tell me? If you are not able to answer, I will answer.
0.1, sir.
Sorry?
0.1, sir.
Actually 15 divided by
Someone is answering 0.1, is it?
terms of millivolts.
Yeah, in millivolts you have to tell me.
1000 millivolts, sir.
And how did you get 1000 millivolt?
15 divided by 2 power 8 minus 1.
2 power 8 minus 1, right?
Yes, sir.
How much will you get?
238. Sir.
Sorry?
238.
This value is 238.
Answer.
But there is
238.
no option of 238, no?
Option D.
Just check. So this is 15 divided by 255. Anyone?
58.8, sir. 58.82.
Correct. 58.8. Correct. 58.8. Did anyone have any problem in understanding this? Does anyone want me to repeat? I can repeat.
Sir, please repeat it, sir.
Okay. So it is like you have one A to D converter, okay? Here one signal is coming which is from 15 volt to 0 volt, okay? Now it can be from 7.5 to minus 7.5 also. The range is 15 volts, okay? This is important. The range is 15 volts and it gives an output of 8 bits, 0 to 255. So what it means is in this range you are supposed to cover this 15 millivolts, okay? So what is the resolution? And resolution means what is the significance of 1 bit. So for example 0 to 1, 1 to 2, like it can go up to 255, okay? Now this covers this full range of 15 volts. Okay, so what is the voltage between any 2 points? So that is the reason you have to divide 15 divided by 255. Okay, and whatever you get, that is the, so this is the smallest change that will happen when there is a 1 bit change. Okay, was it clear?
Yes, sir.
Okay. Okay, maybe I can try out next question. 6. Can anyone answer 6?
Irreversible, sir.
Sorry?
Irreversible, sir. C, sir, answer.
Is anyone answering or talking?
C, sir, answer.
C,
Yes, sir.
which is true. Now, this requires from sampling theory. Okay, so in sampling theory, what it is said is, so if we see this, if you have a signal, okay, you sample it, okay, sample at points, and let's say the original signal was having a spectrum like this. Right now it will have spectrum like this, same, what, fs by 2 at fs. Okay, so this is the main, this is called sampling theory. This is called sampling theory, right? So this is very important. Question number 7.
6 is a C, sir. A, only A.
Sorry?
6 answer is A, I think. B also, correct?
I'm not able to hear you.
So 6
Irreversible, sir, answer.
Sorry?
Irreversible, sir, answer. Quantization is a irreversible process.
Yes, but can anyone tell me why? Why quantization is a reversible process?
So,
Yeah, tell me.
while encoding, basically we will try to round off the figures. Like
Hmm.
1.5 can be 1.6 can be taken as 2, or 1.3 can be taken as 1. But in the decoding process, we can't able to see the exact value. So,
Yes, so yes, Shai is right. So I will just rephrase her answer in a different way. So let's say 1.3 also becomes 1. 1.2
uh,
also becomes 1, right?
yes, sir, just taken as an example.
Correct.
Uh,
Yeah, go ahead. You want to give one example?
no, sir, you can continue.
Yeah. So 1.3 becomes 1, 1.2 also becomes 1. So if I give you this number 1, you will not be able to tell me whether it was originally 1.3 or 1.2. Okay. So that is the reason it is a irreversible process. Okay, question number 8.
True, sir. Yeah.
Hmm?
True. Arduino processor, there is a separate storage and for data and instruction. This is Harvard architecture.
Correct. So should it be A or B?
Yes, sir. Yeah. True.
Okay, good. Yes. So can you repeat what does Harvard architecture mean?
Harvard architecture means there is a separate memory for storage of data and instructions program.
So what is the advantage? Because
Advantage,
extra memory, so your cost is also going high, na? So what is
cost
the
is
advantage?
high. Processing is fast, sir. Speed is more
How
as compared to,
how?
because we are using separate memory for data and program.
Yes, but how does it help? True, you are going in right direction. Absolutely correct. But how does it help?
Don't know, sir. Can you explain, sir?
Yes, Alex. I wanted to tell that only. You see, it has got a separate bus. Okay.
Yes.
So it has, this is your data memory, and this is your instruction memory. Just hold on, let me. Yeah, so this is data memory and this is instruction memory. Okay, so you have separate bus. Now you see, let's say when the microprocessor, this is MUP means microprocessor, okay, when the microprocessor is taking data from this instruction, it can parallelly in the same cycle store data through this bus.
Yes, sir.
Yeah. So that's why both the operations are happening parallelly at the same clock cycle. In one Newman architecture, what happens if you have this, you have only one memory. So instruction is coming here. Now when the instruction is coming, you cannot operate on the data because the data bus is different. Data bus is same, right? So
Yes.
when you are not having separate data bus, you are losing on the clock cycles. So that's why von Neumann architecture is slower than Harvard architecture.
Yeah,
Got it?
yes, thank you, sir.
Yeah. Yes. So what about question number 9? Question number 9. Anyone?
Binary search, sir.
Yes, binary search, but can you tell me the reason? Shiny, you are right, absolutely right. Can you tell me the reason? Just think.
I just remember like successive approximation. Basically, it's on order of n.
Okay.
So
No, matlab, you are going to the answer first and then you are. So, yeah.
it's not linear, sir. But
Yes, yes, I understood.
that
So,
was for sure. So that's
that's okay,
why
that's okay, that's okay.
I didn't pick up
So,
C.
yeah, so I'll try to explain. Okay.
Sir, in successive approximation, we are taking trial and error method.
Trial and error, okay. Is it trial and error or divide and conquer?
Divide.
Correct. So what you actually do in your successive approximation is, let's say that you have a 5 volt, okay. First, what you do is you make one binary, okay, which is very high, okay, and then you compare with this 5 volt. Now, if you see that binary is less than 5 volt or greater than 5 volt, based on that, you set the next bit, okay, 1. So you see from here what is happening is you are first coming into the middle, okay, then you are coming here, okay, then you are coming here. So with every iteration, so first what you do is you try to find out what is the mid value, okay. Now from this mid value you try to find out what is the mid value of this 2. Let's say the mid value is 5, okay. If it is less than 5, it is fine, okay. If it is more than 5, then you try to go to 7.5, okay. Let's say the total range is 0 to 10, you go to 7.5. If it is less than 7.5, so what it means is it is lying between 5 and 7.5. So it will try to come to around, let's say, 6.25. Okay. Now whether it is more than 6.25 or less than 6.25, based on that it will either come here or it will come here. So you see it is constantly targeting the mid value, right? So that's why it is called as binary search. Okay. So these are all terms which are very important. I would always suggest that you read, okay, about binary search, linear search, what are all this. Okay. These are
So basically, it means like it will take first one bit, and after that, it will see whether the next one is higher or lesser, and depending upon that, it will take the 0 or 1
right.
aside. Yes.
Right.
Okay. Yes, sir.
So you see that, for example, let's say you have 8 bits of total. First, it will try to set in this 8 bit only the first bit. Now, the first
Yes.
say set in 8 bits, what it actually means is you are going to the value of 4. Okay.
Yes.
So
Yes.
instead of you check with 4. Now after that, what you do, if it is less than that or greater than that, based on that you either set this bit,
Yes. If it is
this bit. So this is the
okay.
way it will either go to 4 or it will go to 6, like
Huh.
it will count. So that's why it's
Yes.
called binary search.
Okay. That is why it will take n number of.
That's why it will take n
Yeah.
iterations.
Yeah.
Correct, absolutely.
That one I remember actually.
Yes, true. And that is very important, okay?
Yes.
That is very important that you have to
Uh,
know that which complexity is of what order.
yes. Yes.
Try to read more in
I
detail.
remember this method also, sir, but actually, I came through options this time.
No problem.
Okay. Can you give example of the linear search like?
Yes, linear search is simple. Linear search is, for example, let's say you have 0 to 10, okay? You go linearly, okay? Instead of coming to the mid,
Mm,
going, which happens in binary search, you go linearly. You first go from 0 to 1 and you check whether 1 is less than 10 or not.
mm,
Okay. Then you go
okay.
to 2, then you go to 3, then you go to 4. Now the problem with this kind of search is, for example, if you have number which is, let's say, very, very high, then
Your number.
very high, right?
Yes. Yes, sir.
So that is the reason linear search will take time. So it is but it
Time.
is straightforward. Okay.
Hmm.
As complicated as binary search. It is very straight.
So dual slope converter is there, no? So that one is linear search.
Which one? Which one?
Dual slope.
Dual.
Dual slope.
It's a AD converter, right?
Yes, sir.
Dual slope converter is yes. Yes. It is.
Huh.
It is linear.
Linear one. Yes.
So question 10. Any idea? Can anyone tell me what PWM is? See, the way we will discuss, we'll take one question and we will try to. Yes, please. I'm sorry, I'm not. Dheeraj. Okay, yes, Dheeraj. You have raised your hand.
Hello?
Yes.
Sir, second one you tell, sir. No.
Second one means?
Sir, ninth one, sir. Tenth one, sir.
Yeah, 10th one, I am asking the question.
Yes,
So
sir.
you are saying the answer is second one, B.
Yes, sir. Second one, B, sir.
Okay. But can anyone tell me first what is PWM?
Don't know, sir.
Yes, Dheeraj? Yes, if anyone doesn't know, it is fine. Okay, no problem. See, not knowing is absolutely okay as long as you know what you don't know. Okay. If
So
you,
in pulse width, basically, I think with the increase in the amplitude, the width of the pulse will be varying.
yes, right. Anything else? Okay. So what you have told is around, no, it's right, but we will try to elaborate that. Okay. So you see that in pulse width modulation, let's say you give 2 volts. Okay. When you give 2 volts, you will get a pulse. For example, you get a pulse like this. When you give 3 volts, at that time, the pulse will look like this. You see, the time period is constant, right? The time period is always constant. Okay. But the on period of the pulse, it is increasing. Okay. So that is very important. Okay. So you see that it helps in both A and B. Why? It decreases the overall heating of the device. Why? Because if you had given 3 volts continuously, you would have taken I square RT, right? Device. But right now you have some off period here. This is my off period. This is my off period. So when you have off period like this, the overall heating of the device reduces. Okay, and it also regulates the average power applied to the device by varying the DC. Okay, because as you can change the width of the pulse, you can vary the DC voltage. So it is both A and B. Any questions, or should I repeat? Let me know.
Sir, if
Yes.
we decrease the amplitude, then only it will try to reduce the heat of the device.
It will try to.
I didn't understand, like PWM will decrease the heat if we reduce the width of the pulse.
Yes, yes,
Yeah.
yes.
Okay.
It will. Yes, but you see that even if you decrease the width of the pulse, there are places where there is no pulse, right? Because it is 1010, right? So the places where it is 0, you are not consuming any power, no?
Okay.
So the overall,
Yes.
heating is less.
Okay, sir.
Okay.
Hello, sir.
Yes, tell me.
Sir, can you explain this beat rate and baud rate and
Kashiraj, your voice is not audible.
Sir, can you explain this beat rate and baud rate and the relation between beat and baud rate?
Very good question. Very good.
Okay, sir. Okay.
For that, I'll just hold on. Stop sharing. You're able to see the screen, right?
Yes, sir.
Yeah. Okay. So let's say if you have a pulse like this. Okay.
Okay, sir.
So the difference between this. Acha, can you tell me what is this pulse? If I ask you to write in terms of 1010, can you tell me what is this?
This is a 10101, sir.
Okay, 10101. Anyone else? But if someone tells you that this is not 101010, if someone tells you this is 1100110011, is it not correct?
That is also possible, sir.
Correct. So this 11001100, this is also possible, right?
Yes.
So without the help of a clock, you cannot tell me that what is this actually, this rate.
Yeah.
Okay. So that time,
Yes.
So what happens is, let's say you are passing one information which is 10101. Okay. So what you do, you pass it like this. Okay. 1 you represent like this. Okay. And 0 you represent like this. Again 1 you represent like this. 0 you represent like this. Again 1 you represent like this. Okay. So you see that how many signal changes are there in 1 second. So this is, so in this we have 1 bit, right? In this we have 0 bit. We have one first bit. We have again 0. We have again 1. Okay. We have something like this, 10101. Okay.
Yes.
So when we have something like this, 10101, so what will happen is, you see in this 1 there are 2 signal changes, right? It is going from 1 to minus. This is, let's say, 5 volt, so this is minus 5 volt. So it is going from 5 to minus 5 volt, no?
Yes.
In 1. So the number of bits that you are passing per second is only 5. So this total is 1 second. So in this 1 second you are sending only 5 bits. But how many signal changes you are sending? You are sending 1, 2, 3, 4, 5, 6, 7, 8. So the baud rate is 8 bits per second. Okay. So baud rate is the number of signal changes per second, and that is different from the bit rate. Now in this case where you say that this is 10101, here the baud rate and the bit rate both are same.
Yes.
Okay. But not in this case. Okay. So that's why there are different various methods of line coding. So this is NRZ line coding, then you have Manchester line coding. So all those line codings are there. Okay. So just keep that thing in mind. It is very important. Anything else? Any other question?
Sir, do we have any formula how which gives relation between bitrate and baud rate, sir?
That depends on what kind of line encoding you are having. Without the help of line encoding, I mean, so no one can tell that what is the formula.
Oh.
It can be anything. It can be anything. So, I mean, there are cases where the baud rate is twice the bit rate. Okay. And there are cases where the baud rate is some 1 point something, let's say a fractional value into the bit rate. So without knowing what is the line coding, it will be impossible to say.
Sir, can you discuss this question number 1 from assignment number 4, sir? This is based
Question
on
number?
question number 1 from assignment number 4, sir. This is related to this one, the bit rate and baud rate.
I am not supposed to discuss any assignment questions, but tell me, question number 4?
Question number 1, sir, from assignment 4, sir.
Okay. The bit rate of a signal generated from an 8-bit generator is 3200 BPS. Yeah. So it is like.
Yes, sir.
Yeah.
Answer, I think it is 400 baud per second, sir. 400 baud per second. Baud rate.
Bit rate of a signal generated from 8-bit generator. So is it 400 baud per second or 25600 baud per second? See, the answer is either A or B. Okay, but I cannot tell you the correct answer because it will be against the rule of NPTEL.
Okay, sir.
Okay, but it will be either A or B, and I can tell you, just think on this matter very, very carefully. Should it be a multiplication or should it be a division?
Okay, sir.
Okay.
Okay, thank you, sir.
Yeah. So, any other question? If you have. Okay. Question number 11.
Sir,
Yeah.
once again tell me operational amplifier, sir.
Operational amplifier.
Operational amplifier, sir.
Yeah. So you want to know what that is?
Yes, sir.
Okay. So operational amplifier is an amplifier. Okay. So this is an amplifier with which, so the symbol looks like this. Okay. So with which you can do various operations. So when I say various operations, I mean plus, minus, multiplication, log, everything. Okay. So this is what is called as operational amplifier.
So,
yeah, tell me.
Your screen is not visible.
Okay. Just hold on. Just let me see whether enter screen. Is the screen visible now?
Yes, sir.
Yeah, okay. So operational amplifier something looks like this. Okay, the symbol is like this. So you have minus, plus. Okay, you can give any signal 1 and signal 2, and with the correct circuitry, with the correct network, you can achieve any functionality, plus, minus. Okay, so what is your background? What is your discipline actually? Saligari, Manasa, I think you are the one to ask this question, no? What is your background? Are you from electronics or are you from some other discipline?
Yes, sir.
No, you are from electronics or what?
Yes, sir. Electronics.
Okay, okay. So see, in electronics, if you have not studied, you will study it. There is something called operational amplifiers. Okay, so operational amplifiers, something looks like this. So the common term is op-amp. Okay, so here you have some minus plus, you have some feedback resistor. So it looks like this. Okay, and it has got infinite input impedance and very low output impedance. So that's why it is basically a voltage amplifier. Okay, so this is the whole idea of a op-amp, operational amplifier. The basic books to study operational amplifier will be something like Gaikwad. Okay, Gaikwad, study this book. I think Gaikwad, or another book is there which is called Cedra Smith. Okay, just study about operational amplifier. Okay, but I can give you the very basics. So operational amplifiers are used so that you can perform any kind of operation on analog signals. Okay, so that is the reason that it is used for A to D converters, because it converts an analog signal to some digital signal. So op-amp, though it operates on the analog signal, it can give out some analog signal, it can still give out some digital signal also by making the op-amp work as a comparator. Okay, so this is very important. Okay, yes, anything else? I can tell you the books, maybe you can read the books and come back and ask me in the next session. Okay, Cedra Smith would be a very good book. Can anyone tell me this one, quantization error of 6-bit? Hello? Anyone? Anyone who is doing? Is anyone doing? Okay. See, normally what happens that whenever you have some signal, okay, you have this signal, right? So you quantize, okay, you divide the whole voltage into some kind of gaps, and you quantize the data. Now this quantization error can be anything, but the average quantization is whatever resolution you are having, that resolution divided by 2. Okay, so that is the quantization error. Okay, so can anyone tell me what would be the quantization error? First find out what should be the resolution.
Resolution is 158.73.
Sorry.
158.73.
It is in millivolts or what?
Millivolts.
Okay, 158.73. So what should be the quantization error?
79.37.
Correct. 79.37.
37. Yes.
Okay. So always remember that quantization error is resolution divided by 2. Okay? Can anyone tell me what is the Nyquist rate? Okay, so I'll tell you that Nyquist rate is the rate at which you should sample one signal so that it can be reconstructed easily. So what you do is you have one signal, you apply Nyquist sampling and you convert it into a digital signal. Okay, now from the digital signal, if you want to reconstruct the same analog signal, that is possible only when the sampling rate here is twice the maximum frequency that is present in the signal. Okay, so for this one, what should be the Nyquist rate?
68, sir.
Correct. So 68 will be what?
The Nyquist rate.
Absolutely.
Highest
So
frequency.
Highest frequency and frequency
Nyquist
is
rate will be
34,
136.
34 and the Nyquist rate will be 68.
correct. So highest frequency will be 34. Someone said that the highest frequency is 68. See, this part 68 2 pi t is written as 2f pi t, right? So you
Yes, sir.
have inherent factor of 2. So that's
Yes,
why
yes.
this f is 68 by 2, which is
By 2.
34. Okay?
Yes, sir.
34. So 34 into 2 will be 68. But you tell me one thing, I'll give you a very easy problem. Okay, so let's say you have a sine wave. Let's say this is very interesting. You have a sine wave. The frequency of this sine wave is 100 hertz. So what should be the Nyquist sampling rate?
Greater than 200.
Greater than 200. Very well. Is greater than equal to or greater than?
Greater than or equal to, sir.
Okay, so I can sample at 200, right?
Yes, sir.
Okay, so if I sample at 200, let me sample. So let's say one person has sampled here, one person has sampled here. So this difference is 200, right? So you get a final signal which looks like this. Okay, but let's say that someone samples the signal here. Here, what will be the output? The output will be continuously 0. So greater than equals to 200. Is it correct or wrong? You got the funda, no? Why it should be 0 0 0 0 0? Right? So always remember that in case of sinusoid, it should be always greater than 200. Okay? Just keep this in mind. Okay, anything else?
Sir, it should be greater, sir, or greater than or equal to, sir.
See, it is for the ideal case, it is greater than equal to, but for the
Okay.
actual case, it is always greater than. So, for example, if your signal is, let's say, 100 hertz, you should always sample it around 5 times of that. Okay, so that is the real time scenario where the signal is sampled at 5 times the frequency, maximum frequency. Okay, so any other question?
Sir, once can you explain me the difference between Harvard, Princeton, and architectures?
Harvard?
Princeton and von Neumann architectures.
I think this Princeton and von Neumann are same, no? Someone told me last time.
Yes, sir.
Yeah, Princeton and von Neumann is same.
Same.
So it is like you have to understand the difference between a Harvard and a von Neumann. Okay, so let's say that you have this microprocessor. Okay, so microprocessor will have an address bus as well as a data bus. So data bus is bidirectional. Okay, address bus is unidirectional. Now you have one single memory. Now this is a typical von Neumann architecture. Okay. Now you have Harvard architecture. Harvard architecture looks like this. You have microprocessor, you have address bus. Now you have separate data bus connected to one memory and another data bus connected to another memory. Now this is called as instruction memory. Okay, and this is called as data memory. I'm not able to Right. Okay. Just hold on. Okay. Yeah. So this is your instruction memory. And this is data memory. Okay. So in data memory, what happens is you write some address, and then let's say what happens, let's say you are doing a multiplication, A into B equals to C. Okay. So you see, sorry, A into B equals to C. So what happens is you fetch A from this instruction memory, you fetch B from this data memory, and then you write the value C into the data memory. Okay. Now while you are writing the value C into the data memory, parallelly you can fetch the instruction also, the next instruction. So in one cycle you are storing the data, you are fetching the instruction. But in a von Neumann architecture, you take data A, take data B, you put back C, and then you fetch the next instruction. Okay. So there is a one cycle, so everything happens over cycle. So there is no multi-processing in one cycle. But in Harvard architecture, you have multi-processing in one cycle, and that is the reason it is faster than von Neumann architecture. Is it okay?
Okay, sir. Thank you, sir.
Yeah. Yes, any other questions if you have regarding anything that you have not understood? See, this is a question answer session. So, I mean, this is, if you have any doubts apart from the assignments also in the lectures, please let me know.
Sir, how can we differentiate between an ASIC and a PLD?
Yes, so PLD is programmable logic device. ASIC is only one time programmable. Okay, see the ICs that you buy normally, that is called an ASIC. That is application specific IC. Let's say the decoders that you are using, so they are all ASIC. Okay, and that is application specific. Okay, so you can program it only one time, but a PLD is programmable multiple times. So because it is a programmable logic device. So that is the basic difference between ASIC and PLD. Any other thing? Just hold on.
Sir,
Yes.
you told that you will convey the FPGAs that we can buy and do it on our
Yes,
own.
FPGA, right?
Yeah.
So can you buy? I am not sure whether you will be able to buy, but because you all are students, so
And
board.
no, sir. Actually, I can able to purchase or I can work in my lab. Actually, I'm a faculty. Recently, I've joined as an assistant professor,
Okay, okay,
so
great.
I can find it in the lab.
Yes, yes. So you can buy this basis board.
Can you please give it in a chat
Yes,
box?
I have sent. I have sent in chat.
Okay, sir.
Since you are professor, I should call you ma'am instead of.
No, sir. I have been tired of listening, man. I have just joined as a professor, so.
Acha. Nice, nice. Yes. Any other questions? Okay, so let me ask you one question from embedded systems. Okay, what is DMA? Anyone? Okay, so DMA is direct memory access. Okay, so what happens is normally when let's say that you have your microcontroller, okay, and the microcontroller is busy doing some operation. Okay, it is taking the data from the instruction memory and executing. At the same time, some external data is coming. Okay, so what this microcontroller does is it gives up the control of the memory, and the controller, whichever is there, it takes the control of this data bus and puts the data directly to the memory, okay, without the intervention of the processor. So that is called as DMA, direct memory access. Okay, whatever terms I am using here, please make sure that you study in detail, and maybe if you have any queries, just let me know. But yes, this is what is DMA. Okay, so have you started studying VHDL? By the way, Shiny, this basis board is a FPGA board. Okay, that is not a microcontroller board.
Okay, sir.
Microcontroller board or a basis board?
FPGA only, sir, actually.
Yeah, so basis board, yes.
Okay.
So yeah, but how many of you have started writing Verilog or VHDL? Tell me, sir, exam pattern. I don't have any idea of exam pattern because I am not appearing for the exam, so I do not know anything about the exam pattern. But what I know from others is it is MCQs and maybe true-false questions.
Sir, actually, I have worked on the embedded C, like I worked on the field microvision that boards are there. No? During my
Okay,
MTech,
great. In ARM, right?
yes, processor. I only had that experience, even though the specialization is in image processing and embedded. So we have more core on image processing domain only. So,
Okay.
that is why
Yes. No, then for image processing, no, image processing FPGA will be really nice.
Yes, so basically I have more core knowledge on image processing, and embedded is like a little bit of
Yes, yeah,
down.
that is
So,
okay. That is okay. So I'm sure that many of
actually, I'm preparing for the interview for the DRDO. So
okay.
that's why, since I have the specialization, I need to be a little bit of command in this subject, right? So
Yes, then
I
you
need to know
need
the
to know
little
some.
fundamentals.
Yes,
So
then
that's
you need to
why.
know something about FPGA and all, because that is
Yes.
image processing right now mostly happens in FPGA. So
Um,
that's all. So fine then, if you don't have. Acha, how many of you have started working on VHDL or Verilog? You have not answered. Please start working, okay? I think sir is teaching VHDL or Verilog in the lectures. Let me see. VHDL. Sir is teaching VHDL. Then study VHDL, okay? Study VHDL, and most importantly, just make sure that I don't think any assignments are there in VHDL, but start. I have given one board, basis board. So if people can afford, try to buy this board and start working on it. Okay. Yes, so if no other questions are there, maybe we'll meet next week. Is it okay, or you want to discuss something else? Nothing? Okay, then I'll be here for half an hour. You people can leave, but if you have any questions, just stay back and ask. Okay? For today, it is over. We'll meet maybe next week. Anyone? Okay, then you can leave. Okay, bye bye. Yes, Aditya.
Sir, in week 4 assignment, sixth question is I have doubts, sir.
Yeah, please tell me.
If the frequency of the incoming signal is to be reconstruct, it sample rate is twice the highest frequency. Yes, sir. Uh, but
But
it
see, here things are different, right? Here it's asking what should be the frequency of the incoming signal. Whatever we have discussed is what should be the frequency of the circuit such that it samples the incoming signal properly. But it is asking what is the frequency of the incoming signal.
incoming.
You got it?
Once explain again, sir.
Yeah, so it says that, see, let's say your circuit, let's say you have a signal, analog signal, which is at F, okay?
Yes, sir.
So the circuit which is used to capture the signal should be running at 2F.
Yes, sir.
Should be more than 2F, right?
Yes, sir.
So if we turn around the question and if we ask, then if the signal, if the circuit frequency is F, what should be the frequency of the incoming signal such that it samples properly? So what should be the answer?
Yeah. F by. Sir, I think F by 2.
Correct. So it should be less than F by 2 or greater than F by 2?
Greater than F by 2.
Why?
Sir?
Why? So let's say I'll put it. You have the frequency of the FC, right? This is the frequency of the circuit.
Yes, sir.
Right? The income signal is F. So F should be, sorry. So F should be less than FC. Okay. Nyquist says what? Nyquist says FC should be greater than 2F, right?
Yes, sir.
Right. But you have been asked that the frequency of the circuit is F. So what should be the frequency of the incoming signal? Okay, so if I consider FC as F and F as Fi, which is the incoming signal, what should be Fi now? Fi should be what? Fi should be less than FC by 2, no?
Yes, sir.
As per this concept?
Yes, sir. This correct only, sir.
Correct. So it should be, so which should be the correct option?
less than f by 2, sir.
Correct.
Sir, I have one doubt on resolution also, sir.
Yeah, tell me.
We want to calculate in millivolts, yes, sir.
Which one? Which question?
Uh, Fifth question, sir.
Fifth question.
Yes, sir.
No, I think you have to calculate in volts.
Sir, the formula is 2
Yes,
by...
you have to. Yes. Yes, it says in millivolt, na? Calculate the resolution in millivolt.
Yes, sir. Sir,
The problem that you are facing?
2 by 2 power n minus 1, you said, sir, formula.
Correct.
But it asked in millivolts to calculate, sir.
Yeah. So it is 15 divided by 2 to the power 4 minus 1, right?
Yes, sir.
So 2 to
One the answer.
Sorry?
1.
Calculate just one answer, sir. 15 by 2 power 4 minus 1.
Correct. So it is 1. So what is 1 volt, right? So what is 1 volt in millivolts?
1000.
Correct.
Yes. Okay, sir.
Okay.
Okay, sir. I understood, sir.
Okay.
Thank you.
Acha, I have not shared my screen. You didn't tell me. Okay.
Oh.
Sir, 7th question.
Just hold on. Yeah. 7th question. But I can only give you a hint, okay?
Sir, is the question is wrong, sir?
See, when the question was made, no, it was long back. So at that time, the question was correct. Right now, the question is not very much correct.
Yes, sir.
Okay. So, but this is a direct question, so I cannot answer the question. I mean, it will be against the rules to answer the question.
Yes.
Is Aditya any other thing?
No, sir.
Okay. Anyone else?
Sir, can you explain 9th one, delta sigma?
But again, it's a direct question, no? Means I have to directly tell you the answer. The problem is that, see, if it is a mathematics question, I can give you some hint, but this is a direct question. So first, you want me to talk about delta sigma?
First, explain delta sigma modulation, sir, so that.
Okay, so delta set, just hold on, then I will do it properly. Okay, so yes, just hold on. See how this delta sigma modulation work is. You have one input signal, okay, which looks like this. Now what normally A to D converter does is it takes one sample and it converts to a digital wave, okay, digital bit pattern. Okay, but delta sigma does what is it stores this bit pattern, okay, and it calculates the difference between the last analog value and this analog value. It calculates only the difference. Now this difference, what it modulates, with the help of this difference, what it does, it converts this difference into a series of bits, and whether it is more or less than that, depending on that, it will either add here or subtract from here. Okay, so this is called delta sigma modulation. Now this is also named as a recursive filtering. So right now, based on this, you can, find out what should be the answer. Is it okay?
Okay, sir.
Yeah.
Sir, I have doubt on first question, sir.
First question, you have doubt?
Ha, sir.
Yeah. See the bit rate of a signal generated from an 8-bit generator. Okay. So you see the bit rate. So all the 8-bit generator, all the signals in those 8-bit is getting generated at 3200 bps. Okay. So what will be the number of total signal changes that is happening per second? Okay. So normally it is a multiplication. Is it okay? See what happens is, if you understand this, what has been said is it is an 8-bit generator. Okay, so it generates.
Sir, for that I think B is the answer.
Sorry.
For that question, I think B is the answer, sir.
No, I'm not able to hear you. Hello. Hello. So it's like that 8 bits are there, right? It's an 8-bit generator. Now all these bits are getting generated. Okay. Now this is 3200 bits per second. So in 1 second, 3200 bits are being generated. Here also in 1 second, 32 bits are being generated. Okay. So 3200 bits are being generated. Now you tell me that in 1 second here, what should be the number of signal changes per second if you collectively think? And based on that, you say that is a baud rate, because baud rate is signal changes per second. Okay, and bit rate is information changes per second. Okay. So normally baud rate is more than the bit rate. Did you get it? Hello?
Okay, sir. Thank you, sir.
Okay. Yes, anyone else?
Sir,
Yes, Aditya.
sir, I have doubt on fourth question, sir. In a flash ADD converter, it has 3-bit conversions. 2 power n is the formula.
2 to the power n or 2 to the power n minus 1?
2 to the power
2
of
to the power n minus 1, sir.
Yeah. So what should be the answer?
7.
7, sir.
Yeah.
Okay, sir.
Yeah.
Sir, can you explain Nyquist criteria, sir?
Yeah, Nyquist criteria is, so let's say you have a signal, okay? You have a signal. Now it has to come through ADC, right? If you want to digitize the signal, if you want to digitize the signal, it has to come through ADC. So at what rate this ADC sample this signal such that the reconstruction, the digitized signal will actually replace the analog signal. Okay, so this is called a Nyquist rate. Nyquist rate. Okay, and this is same as twice the maximum frequency of the signal. Okay, and it is normally greater than twice the maximum frequency of the signal. Just hold on. Okay, so this is called Nyquist sampling frequency. Okay, now so in this way, so for example, let's say you have a circuit which is working at f, so you have to make sure that your incoming signal is less than f by 2. So this is called as Nyquist sampling frequency. Is it okay?
Okay, sir.
Okay, anything else? Any other questions? Okay, fine. Then I'll see you next week. If you have any questions, please ask.
No, sir.
Okay. Okay, then I think you guys can leave. Okay, Dheeraj, Shiny, Aditya, any questions? Jinka, Manasa, Rohit.
So,
Yes, time.
can you give the important topics for this subject to prepare for?
See, I
Otherwise,
think the important topics now it is covered by sir only. Whatever is covered by sir, nothing else will come in the actual exam. Okay.
I'm not asking regarding exams, sir.
Then.
Regarding interview purpose.
Acha. Okay, okay. So you see, since you have asked for image processing, so how much do you know about image processing?
Image processing, like regarding topics or like.
Yeah, topics. I mean, like the edge detection, corner.
Yes, edge detection, linking, segmentation process basically, and
Yes, yes. So you
classic image classification is my project, sir. Actually,
image classification with what?
acoustic scenes and events. Basically, I have done the project by taking the audio samples,
Hmm.
which are the one-dimensional signals.
Correct.
But I have converted them into the two-dimensional Mel-scale spectrograms,
Yeah.
and I have done the classification upon the images.
I understand. But then
Uh,
when you are doing classification, are you using some neural network?
yes, sir.
Okay. So it is CNN, right?
CNN, convolutional.
Yeah, okay. So I mean they will ask you about the see on the last, I think classification you have used cross entropy as a loss function.
Yes, sir.
Yeah, so maybe they will ask you about the loss function and different, let's say Otsu's binarization process, okay? So the thresholding process where you actually do a binarization of the image based on the thresholding. So that is a very important thing. Edge detection, corner detection, like
Okay.
private filters.
Private
Very
filters.
important. Learn about all the type of filters, okay? And
Okay.
segmentation is very, very important, and then spectrogram. So can you tell me how the spectrogram is generated? Just for example, if someone asks you in the interview panel, how will you say?
Spectrogram, like using the uh, discrete cosine transforms.
No, it is see MFCC is uses discrete.
MFCs are Mel scale as well
Correct.
as log Mel features as well.
Correct. So that is used in MFCC, but in STFT, if you take only the STFT, it is like a fast Fourier transform operating on samples. Okay. So
Okay.
basically, it is like a DFT of all the samples. So just make sure that you know about STFT and MFCC in detail.
Okay, sir.
That is very important.
And regarding data augmentation techniques, also like improving the hyperparameters inside the network.
Yes, yes. Hyperparameter tuning, right?
Yes, sir.
Yes, yes. I mean that doesn't come under image processing. That comes under convolution.
Convolution, that part also I am asked to do.
Yes, yes. They will ask. Learn about TensorFlow.
Okay, sir.
Learn
Okay.
about TensorFlow.
Okay, sir.
Yeah. This must.
Basically, I am 21 passed out, and after that, I have given NET exam.
Okay.
Then after, I'm waiting for the results actually, DRDO results. Meanwhile, I don't want to be sit idle.
Oh.
Join
DRDO
that.
results means DRDO written test results?
Return, yes, sir, return
Okay.
it's been done, and I don't want to sit idle. So
That's very good. That's very good. No,
I
keep
want to share
learning.
knowledge as well as I want to learn as well. So
Right, right, right. No, keep learning. Keep learning. That is very good.
fine, sir. I'm also thinking future PhD.
Yeah. But PhD is just like it's a 5-year process, no? So
No, sir. Actually, under my professor, it's 7 years. Gautam Sahar in Kharagpur.
IIT Kharagpur.
Yes, sir.
Arre bhai.
That's why I didn't convert it there.
No, don't get it. It's 7 years is too. 5 years is only too much. 7 years is
My
also.
PhD mentor, she did under him for 8 years. It's her last year when
Oh.
I was doing my MTech. And basically, sir wants to keep the students as much time as he wants, and he will give extra stipend also, extra other than the college ones, because people he don't want to let the people go outside because there are a lot of work in the lab. So like DRDO funded projects are also going on there. So
Acha. Great.
that's why he will keep the students.
No, it's good. But make sure that whenever you do PhD, you have some You don't drag that long. I mean, after
I'm
PhD,
planning for abroad, sir. Actually, after getting into, if I get into DRDO, then by after probation, then I will get the chance to go.
yes, yes, yes. You
So
will
I'm
get the chance.
thinking that way.
All the best. All the best.
Thank you, sir.
So then, if things are now finished, then we'll end up the session.
Fine, sir.
Anything else you want to ask, Shiny? You can ask.
Fine, sir.
Okay. Fine then. Bye bye. Good night.
Bye, sir. Good night.